In the previous lesson, we had talked about a new concept of a random variable, which we always denote with a capital letter, typically x. And then we had got into the idea of modeling this variable with a probability model. So this was a mass function, a PMF, that we constructed, which is essentially just a table of values for the outcomes of x and its probabilities. And then we talked about a cumulative distribution function. And we also talked about the expected value, or the expectation of x. And this is essentially the most likely outcome if we were to repeat the experiment over and over again in multiple trials. Now we're going to follow up today with some properties of expectation, because they're going to lead us and be helpful when we come up with the final important concept to do with probability models. Now, another notation for expectation is this function notation. So we'll call it E of capital X, and we'll write it using the same definition as before. Now, note just some terminology or some notation. This capital X is the random variable, and it takes on these values x1, x2, x3, all the way so on and so forth. So these are the outcomes of the random variable. So that's why sometimes you'll see the capital letter X and sometimes you'll see the lowercase letter x. Okay. Some very important properties of the expectation. For instance, if I ever decide that I want to put in a constant and ask what is the expected or most likely outcome of a random variable that's always going to give me the same value c, well, I think you could intuitively understand that it should just be the value of c, because if the random variable is constant, you should see no deviation from that. But mathematically, when we plug this in, remember, this is a constant. Now, at some point in your life, you should have learned about properties of sigma notation and of summations. And one of the properties is that you can take out a constant. Now, if we were just dealing with summations, we'd have to stop at this point. But we learned last time that the sum of all the probability values has to equal 1 for a mass function. And we're always going to be under the assumption that we've got a mass function. So it makes mathematical sense that we've got that. So the expected value of a constant is just that constant. So let's take another example. So let's say that we take the expected value of some random variable and we get a mu. We would like to figure out the expected value of ax plus b if a and b are constants. And note that mu will also be a constant. Now, this second one is really important because throughout the course, we're going to be talking a lot about just a linear scaling and stretching and shifting of the variable that we've got here. So this type of combination will be important later today and throughout the semester. By definition of expectation, this is just going to be axi plus b weighted by all those probability values. Now again, summation properties let me split up a summation in the following way. So I can distribute this. And as in the last example, if b is a constant, I can write it in that way. And just like before, this thing is equal to 1. But what's really important here is that that's equal to mu. By definition, this is the expected value of that random variable. So we end up getting an a mu plus b. So that's good. A linear function of the random variable just gets reflected in that expectation. A very useful one that you'll need as well. Kind of works out to give you this. And we'll have xi minus mu pi. So I'm hoping that we can see that this will be xi pi minus mu pi. That's a 1. That's a mu. We'll get mu minus mu is 0. So keep that in mind. We're going to need that a little bit later. Now, sometimes we will need the expectation of a function of a random variable. So for example, if I were to say, I'm going to define a new random variable as some function g of an old one. If I were to build its mass function, right, I'd have the values of the random variable here, and its probabilities would be there. So I'd have some P1, some P2, some P3, etc. Now, if I insert an intermediate value, some intermediate function, I would have its values as g of x1 and g of x2 and g of x3. But the point of the story is that these will pair up in exactly the same way that the x is paired up with those probabilities. So regardless of whether I define a new intermediate variable or not, we can come to the same conclusion about the expectation. So if I ever want to take the expectation, or I'm curious about the expectation of some function of a random variable, according to our previous definition, we can just write it down, g of xi weighted by those individual probabilities. It doesn't matter whether I use the original variable or some new variable, they both have the same probability, and that means that the definition of expectation should end up being the same. So that ends up being useful for us a little bit later, but as a simple example, if I ever wanted to say, let's say, take the expectation of this square of a variable, according to what we've got, whatever function of x lives in here, you put its representation right there. So since the function of x that I'm looking for is x squared, its representation for the individual outcomes will just be xi squared. And in that way, we can end up using these expectation properties. So in the next video, we're going to talk about one of the main applications of this, and it's the final general property of random variables and mass functions that we're interested in.